First of all, I will briefly introduce Professor Yin. Professor Jianhua Yin is now Chair Professor of Soil Mechanics and lead of Geotechnical Unit at the Hong Kong Polytechnic University. And he received a PhD from the University of Manitoba, Canada in 1990. Professor Yin has a good track record in research and has played a leading role in development of advanced soil testing equipment, innovative fiber optical sensors, establishing a large-scale, multi-purpose physical modeling facility for studying the geohazards. Professor Yin has received the extensive honors in geotechnical engineering. He was ranked the top 88 among more than 50,000 scientists in the geotechnical and geomatics engineering in the world's top 2% scientists by the Stanford University in 2022. Now we welcome for Professor Yin's presentation.
Thank you very much, everybody, Professor Hans-Peter, and everybody here. Okay, this talk actually, I proposed to NGI, okay, to give for many good reasons. Okay, why I want to give this talk. Actually, on Friday, I'm going to give another talk, but I want to give this talk at NGI. I hope this is my great honor if I have opportunity to give this talk. That's something like is my dream, because my research is related to NGI from beginning, origin. It's my great honor to be here. I hope Susan is here, can listen to me. If Professor Beren is still alive, and he will feel really happy. And his work has been continued by me. Professor, your first director, NGI. Okay, that's the reason. So I'm talking about the nonlinear rheological model of clay soils and applications. I use the word nonlinear rheology. Is a very classic word related to the time-dependent behavior of all the materials. A soil is one of the materials. And I emphasize nonlinear because the early days, rheological models are nearly all linear, no good for soils. Because the behavior of soil is nonlinear from beginning. So how to extend linear model, rheological model to nonlinear is not simple, I tell you. But I have done it. Okay? Based on the work of Professor Beren, the first director in NGI. So I don't want to go through this one. I will go one by one. Time dependency. I want to save time on this one because the people here, the materials, many materials have a time dependency, including clay soils. Okay, soft soils you encounter in Norway. Okay, I don't want to emphasize you are experts. I have worked in this area for a long time. You forgot the control. Okay, and one example is the settlement of Tower of Pisa. Oh yeah, why is this? I think I said probably autoplay mode. I hope it's not moving. Okay, the Tower of Pisa, you can see settled in the soil more than 3 meters and inclined. And I visited this site in 2000 with my family, my wife and my son. I took a photo on the joints surrounding the site. At that time, the Tower of Pisa was...
Sorry, share. We didn't share this presentation online.
No, I can see that.
Okay, so it's
you can see online. Okay,
yes,
so it's working. It's online.
I think so.
So this Tower of Pisa is a good example of structure on soft soils, settled more than 3 meters, inclined more than 2 degrees. And if you go to the joint was taken by me. Okay, when I visit the site, you can see the clay, a sandy clay silt, upper clay, and also clay below. So there are layers of clays. That's why this tower settled more than 3 meters. Okay, now the tower has been stabilized. I don't want to say that. Another good example is Kansai International Airport. 2 artificial islands, and the 1 island 2, I don't know. Probably I said autoplay mode. Is my problem. So no. Slide show, I think. Slide show. The formula. Okay, sorry about this one. This is island one. This is island one, island two. I can see you the problem of sediment. Okay, excessive sediment problems. And for the first island, okay, when the artificial island is built, that means they place the fields on the seabed up to a certain level, and up to say 1990, okay, the field is up to the level, construction finished. You can see the sediment or not, okay? The sediment continue to increase. And at this year, 1994, the first runway was open, okay, but still big sediment, okay? So big. You know, this is more than 5 meters to here, or more than 9 meters post-construction sediment for this first runway, okay, is huge, okay? I think nobody wanted to see so big post-construction sediment, okay, but it happened here. And some Japanese professors, experts did some calculation predictions, okay, on the first runway. You can see the yellow curve, calculated sediment up to more than 2030, you know, no more than 6 meters, according to prediction. But what we measured is more than 6 meters, is more than 9, okay, more than 9. I showed you that data before, more than 9 meters. A big difference, okay, 9.1 meter minus 6, the 34% of difference, relative error. So certainly something wrong, okay? And I believe something wrong with the calculation method, okay? Calculation method, sure. So I visited this runway 1 in 2008 together with Professor Richard Jardine in Imperial College and other committee members. I went to the basement and they jacked up the columns and put a steel plate on the bottom to compensate the sediment. In this way, nobody likes this. They have no good choice. They have to do this one, okay? Something's wrong actually from the beginning, the design and construction, okay? This is the issue, okay? This is the first runway, the second runway. When at that time I visited this island, the second artificial island was under construction. So they learned a lesson from the first runway construction. So for the second runway, they apply surcharge longer, wait for the sediment to occur longer. Okay, so that you can see the sediment for the second island is bigger. You can see up to here, up to 2012, is more than 40 meters. More than 40 meters is bigger than the first runway, because the second artificial island is further away from the shoreline. And also, I believe the field materials they put on the seabed is probably higher, so that the total sediment is bigger than first island, but they wait a longer time, let the sediment to occur, denote the ground longer time, so that the post-construction sediment is smaller. Okay, so this they learn a lesson. So okay, so the post-sediment is much smaller. So for us, we have to control the post-construction sediment. Okay, just they learned the lesson before. Or we need the sediment. Okay. In Hong Kong, we have some problems. I don't want to repeat at the same time. We also see many problems, okay, sediment in Hong Kong. And what's a creep? Okay, creep is a phenomena we observe, is a phenomena. So creep is a continuous deformation of sediment on the constant load. That's the definition of the phenomena. And creep can occur in the different materials. Here we deal with the clay. Even for plastic, for other materials which can also creep for different materials, okay? But here for creep itself is a phenomena, okay? It can happen to different materials, okay? So creep is a phenomena on the constant load. For example, for odometer test, I visited your lab, okay, just a while ago. You had many odometers in the lab. And for a lab, for odometer test, the thickness of a specimen normally only 20 millimeter. Diameter is about 50 millimeter. You apply a constant load. Then you can observe the compression of a specimen gradually with time, nearly infinity increase, but the rate of increase is getting slow down, but no failure because the odometer test is a confined test, no failure, okay? But you can see the time dependency very clearly. Okay, and from the odometer test, you can see a very clear curve. From the data, you know also very well, is voice ratio decrease with time on the constant load. The constant load is keep constant. This is a log scale time. The voice ratio decrease with time, and this is a very clear turning point is here. So people say in this period, okay, this turning point in this period is a primary consolidation period. And after this period is a secondary consolidation period, okay? And this slope is a very famous parameter, a secondary compression or secondary consolidation coefficient defined as the C alpha E in terms of voice ratio and the local time difference, okay? The larger the slope, the larger viscosity of the surface or creep, okay? So this slope is a good indication of the creep. I go quickly, okay? And consider different clays in the world. Okay, C alpha E is different for different clays. And Norwegian, this is a plastic clay, okay? It's 5. It's around here. It's similar to the clay in Hong Kong. Hong Kong is also in this range, okay? For some peat, okay, it can be very high. Okay, for Mexico City clay, it can be very high. 6 is for the peat. Peat is the organic source. It's highly compressible. So C alpha E is very big. So C alpha E gives us an indication of the viscosity of clay soils. Okay, this give you a range, and why clay has this kind of viscosity and creep behavior. I consider many people consider is due to so-called absorbed water. Absorbed water. That means clay surface normally carry negative electrical charge. A water molecule has 2 poles. One is positive, one is negative. So the positive pole of the water molecule is attracted to the clay surface, and which is viscous. Okay, I don't want to go spend too much time. Mainly due to this one, electrical chemical interactions. So creep of the clay is mainly due to visco-absorbed water. Also, people call it double layers, okay? And on the clay particles. Maybe some deformation of clay paste, as considered maybe small clay paste. More important is, I believe, is a composite. Is a visco rearrangement, sliding deformation of clay particle skeleton. I say it's a skeleton structure. Mainly because the skeletons consist of clay particles, and this skeleton will have a very large visco deformations. And basically, we calculate the sediment deformation of soils. Basically, we calculate sediment of soil skeleton. Okay, water itself is incompressible. Basically, the soil skeleton is compressed. Okay, it's mainly is clay skeleton. Absorbed water is not free water. No, it doesn't follow Darcy's law. Okay, absorbed water is the origin of the viscosity of clay soils. Doesn't follow Darcy's law. Okay, and of course we have hypothesis A, hypothesis B. Actually, I will cover more this area how to calculate the sediment. Okay, another talk on Friday. Now, go back to the models. Mathematical models. You know that there are many linear rheological models already in the history. Hooke's law is a linear elastic model. You can consider it probably the special case of rheological model. Consider no viscosity, then this material behavior become elastic. Okay, can be considered a special case of rheological model. You will see that. Newton's visco flow body is considered viscosity of source. Very similar to Darcy's law. Okay, Darcy's law is considered water flow in the pores. Newton's law is considered the visco flow of the materials. Okay, Newton's law, there are similar body is rigid plasticity. This is the basic elements. Then people combine together to create different linear rheological models, including Maxwell model, Kelvin's model, and other composite models. But all this is a linear rheological models. Okay, linear. So my work is extend the linear model to non-linear. Okay, based on new understanding of the soil behavior. Okay, Here, Maxwell model is a very famous model, which is a combination of visco dashboard. This one follows Newton's visco flow rule law. This is elastic elements which follows Hooke's law. The two elements are connected in series. Then we have Maxwell model. It's very famous, but this is a linear rheological model. Kelvin's model is two elements are connected in parallel. Okay, this is the Kelvin's model. Okay, I don't need for me to go to all the details. And for Maxwell model, we can derive Maxwell linear model very easily here. I don't go details. By the way, if people here, people online are interested in this my PPT, you can get it all my files from Dr. Ray. Okay, you can send it to people. Okay, so I don't want to spend time on all the details. I want to more emphasize the concept, the understanding of fundamental issues. So linear rheological model is a connection of a spring and a dashboard in series. Then we can derive a constant model. Is here. Is there constant model? So you can see this is the strain rate. This is stress rate. Here, stress is the effective stress, because we are developing a constant model for soil skeleton, not for total stress, based on effective stress. Okay, this is the elastic part. This is visco part. This is a constant model already, very easy. But unfortunately, this linear model is really not good for soils, or not good for soils. So we need a nonlinear model for soils. Okay. So you can see many combinations of different elements, or many. Okay, I don't go details. And here some Chinese, they did some early work. The two persons, one in China, one in Canada, their original work was to combine a linear rheological model with consolidation equations. To apply linear rheological models to the soils, to consider the coupling of the water and the soil skeleton. So this is their original work. In that time, yeah, that's the first one, they do this one. But they didn't have any model, develop any model, even linear model, they didn't develop their own model. They just apply other people's linear rheological model to consolidation problems, okay? Professor K.Y. Loy is a very famous professor in Western University, Ontario. Go back here. This is what I want to emphasize more is how to read this one, Dr. Norit Berin, the first director of NGI. Okay, you can see, and this is a diagram he published in 1967 in a paper. And this is my PhD supervisor, Professor James Graham. And he did a postdoc in NGI on the Professor Dr. Berin. So that's my connection from here. Okay, the one connection to the men, different people. Okay, one connection. And Professor Jim Graham made a joke to me. I was the grandson of Dr. Berin, according to academic generation. So I was grandson of Berin. So this is a connection to the men connections. Okay, and of course, Professor Graham is quite a part of me because of my original contribution area. I also mentioned beginning, if Professor Dr. Berin alive, I think he should not be disappointed with me because I developed a model based on his original concept. This original concept is this diagram. This diagram is very important, very original work by Dr. Berin. Yes, this diagram looks very simple from the automated test. You can do such a test very easily in the lab, in NGI. I can discuss a little bit more on this one. What's this diagram imply? And what I have done based on this diagram when I was a PhD student. Okay, this is a very important concept. I want to mention to you. You can apply the concept for different soils later by yourself. Okay, this is an automated test. You know that. Conventional automated test, we have a soil specimen here, 20 millimeter in thickness, 50 millimeter in diameter. You apply a vertical stress on the top, keep it constant. For example, this is 5 tons per square meter, maybe up to, give one example for the line. This is 10 tons per square meter. 10 tons, that means 100 kPa. 9 tons, 90 kPa. You keep the constant. Okay, then you can more probably can measure immediate response. Hopefully it's here. Okay, but here you consider this is in terms of year. I prefer make this 1 day. Okay, it's easier to explain. This is 1 day. After 1 day, on the 9 ton per square meter, say this line is 1 day duration. Okay, imagination. Then you can get this point. Then you can wait for a long time, say up to 3 years. Then on the same vertical stress, the soil is compressed. Keep in mind this is Walsh ratio. Okay, Walsh ratio vertical strain is related to each other. Okay, you can wait for 3 years on the same vertical stress, then come to here. Okay, this is depend on the time. If we can wait even longer, 30 years, then come to here. 300 years to here, 3,000 years to here. Of course, no people can live for 3,000 years. This is just imagination. This trend is correct. This trend is correct. Okay, if you could do the test for longer time, the trend is correct. In the geological time, 3,000 years is very little time, right? Geological settlement, okay, in geological history, it's 3,000 years is very short period of time. Okay, this is by imagination and is true. It's true. Okay, this is from automated test. This is a time dependency. It's different time, different strain, or different Walsh ratio. This one. Okay, this is one. If we do the test on the different vertical load, for example, on here, this is a 5, maybe here is 6. You can say maybe 1 day is up to here. Don't worry, this one can go up. Okay, 1 day can go up to here. Maybe 3 years come to here. On the same vertical load, you can do the same test. Keep longer. You can go here, go here, go here. You can do another test. Say 20 pounds per square meter. You can suddenly maybe very quick deformation come to here. Then this is for 1 day. Maybe 3 years come to here. Then maybe 30 years come to here gradually. What I want to say is on the different vertical stresses, and you can draw a curve for the same time. For example, for 1 day, this is 1 day, you can draw a line like this one. Okay, draw a line like this one. But this line is from different vertical stresses, but for the same duration, 1 day. Okay, this is what the Baron did. Okay, if you can draw the line with duration 3 years for different vertical stresses, then you can get a 3 years line up to here. 3,000 years up to here. The lines are approximately in parallel. This is what Baron says the timelines. Okay, timelines. And in his paper, quite interesting. In his paper, actually, Baron mentioned those are timelines. In the paper, he also mentioned one word. Many people didn't pay attention. They mentioned the equivalent time. If I remember, you got to read the paper. In the paper, he also mentioned equivalent time. So this timeline is not an ordinary timeline. It's some kind of equivalent time. He mentioned in the paper. And if you, for example, on this 9 tons per square meter load come to here, come to 3,000 years, then you increase the load again. The curve will go here, go here. If you increase load one by one to here, you can see a very clear turning point, a PC. In the turning point, this turning point is due to aging. The word aging was in the Dr. Baron's paper. Aging means a long time of the creep. A long time of creep. This is aging. Okay, due to aging. Okay, this is very similar to ordinary pre-consolidation pressure. Very similar, but this is not due to unloading. Reloading is due to aging. It's quite interesting. You can see this kind of curve, this kind of timelines. Beneath, okay, of this paper published in 1967, quite a few professors tried to develop a mathematical model. What I want to say is the figure here and the paper, the main contents in this paper basically is descriptional. Like this kind of phenomena is a description of the time dependency. But no mathematical equations, no mathematical models, and so on. And other people wanted to develop mathematical models, quite a number of people, based on this concepts, descriptions, okay? So coming to me, when I was studying in Canada, I went to study in Canada in 1996. And my professor, Professor Jim Grant, gave a few topics needed me to choose. One related to buffer material, okay, the buffer material, sand bedding and buffer materials, which related to nuclear fuel waste disposal, okay, and that's a topic I can choose. And he also mentioned some type-dependent behavior. That's another topic he suggests to choose, because in Canada, in Winnipeg, Winnipeg clay is a highly plastic clay. The type dependency is also a big issue. Okay, this is another topic. After a while, and I decided going to choose a topic related to type dependency of the different clay materials. So I have to choose this topic. Once I choose this topic, I need to review the literature. Okay, find the papers. So this is a paper I find, and also some other related papers also I read. And because of my master's degree was also related to constitutive models, but not for type dependency. We need to constitutive models. So I have some basic knowledge regarding constitutive models. Okay, now here the behavior is type dependent, and how can we develop a mathematical model for this kind of type dependent behavior? So I have to read all the papers, all the papers and so on. So this is a paper I read, and I spend a lot of time to try to understand this paper. I can tell you, I can probably spend a few months, 3 to 5 months, just to think about this diagram in my mind. How can I derive a nonlinear model for soil behavior based on this diagram? Finally, I did it. I show you. So finally, I don't go details. Finally, I derived this very simple constitutive model for one-dimensional case. And this is a Maxwell linear rheological model I mentioned before, okay? And there actually is a connection of a spring, which is elastic, and a dashboard, which is a visco behavior in series. I discussed before, right? Maxwell model based on this one. But in Maxwell's model, the spring is elastic, and the visco dashboard is a linear, is a Newton's visco flow law. Okay, this one is all linear. But my model consider the spring non-linear. You can see the visual comma. Kappa here, you see kappa here, kappa. You know the kappa parameter in ChemK model. ChemK use the same model. Kappa, the V is a specific volume. V is 1 plus initial voltage ratio. Okay, V is a specific volume. Kappa put on the bottom, put all together is a E. All together E. E here is constant, but in my model, depending on the stress. The larger the stress, the higher the modular. You can see this is non-linear. One more thing is this is based on Newton's linear flow law. This is dependent on stress. Eta is a viscosity parameter, which is constant. But in my part here, this is viscoplastic. This is elastic strain rate. This is viscoplastic strain rate. But my viscoplastic strain rate depending on the strain, depending on the stress. Okay, but here depend on the stress only. Okay, this is depending on strain and stress. Okay, when for different this one on the same stress, I tell you, for example, the creep test on the same stress, the creep rate, the visco strain rate is constant. But for my model, this visco strain rate depends on stress and strain. This is clearly wrong. This one clearly wrong. You see, when stress is fixed, the viscoplastic strain rate is constant. It's wrong. I show you. You can see this model again. You can see the stress is constant. According to Maxwell model, when stress is constant, viscoplastic strain rate is constant. Actually not. When the time increase, this here strain rate, viscoplastic strain rate here is larger. They're getting smaller and smaller, even very, very small. So this rate is gradual degrees, not constant. And you can see for here is a stress, here is a strain. This is a strain, stress point. But here, the same stress, but a strain, which ratio related to strain is different. So actually, the viscoplastic strain rate is dependent on the stress and strain point. Okay, so but here, when stress is constant, this is viscoplastic. is constant, is wrong. Actually, this ratio decrease with time. So this item can describe this decrease gradually with time. Okay. So one more thing, I want to go back to this diagram. One more thing, and actually, I developed this one-dimensional model in my thesis. Actually, even for myself, later I still need a few more years how to understand more this kind of behavior. Another really important scientific, I don't say it's a discovery, but I can say we make it very clear. A very important understanding, scientific understanding is this one. Okay, this is different for each timelines. For each timelines, here, the viscoplastic strain rate can be determined. Okay, and on the same timeline, the viscoplastic strain rate is a constant. Okay, it's constant. Okay, each time is corresponding to the constant viscoplastic strain rate. That's one. Here. Another thing is I can get, for example, from A, B to C, I can get a viscoplastic strain rate, and here it gradually decrease. Okay, I can get the strain rate here. You can see I have an epsilon VP dot C and here. From here, I can get a viscoplastic strain rate. I can do another test. Is you can do the loading test from here, then do the unloading to the same point. So this point, you can reach the point through the quick test from here to here, or you can also reach the C point from the loading, unloading, right, to the same point. For two different passes, loading passes, actually to the same point. As not at the same point, the viscoplastic strain rate is the same. That means you can see this is a viscoplastic. Can you see here? Epsilon, VP, and dot. At the point C, it is depending on the effective stress and the voice ratio only. Nothing to do how to get this point. Nothing to do. That's I want to explain this one. Actually, I spent a few more years later trying to figure out, understand this even better. But actually, you can see my equations is consistent. This is viscoplastic. Okay, this elastic strain rate, this viscoplastic strain rate is dependent on effective stress and strain only. Once the strain, effective stress are given at the point, the viscoplastic strain rate is fixed. It's all here. All the parameters, don't worry. This is a very important finding, scientific finding. I don't say it's actually other people have similar finding, but probably they didn't emphasize that much on this one. But to us, that means we can do quick tests to get the viscoplastic strain rate. This kind of viscoplastic strain rate can be applied to any loading process. As long as you know the stress, effective stress strain, then viscoplastic strain is fixed. You can see my equation can give you the answer. Stress and strain is given.
You have a question then.
Okay. Where?
Hello, it's me. Like I'm sick today. That's why I'm not really be there in person. But I have a question on this point. Is it also related on the loading cycles? I mean, like if you load it for several times, I'm not sure. But loading and unloading once and loading and unloading 10 times, do you think that will be different?
This is a very good point. Actually, I have thought this problem for some time before, because I will show you later. For my results is for static test. I mean, it's loading, unloading, but not frequent unloading, reloading. Okay, that's related to your cyclic loading, and you will see later my unloading, reloading curve is the same line. But on the cyclic loading, you can normally see a loop. So I consider cyclic loading can add another factors to the stress strain time dependent behavior. Cyclic loading, I consider, okay. You can see my explanation. The creep is mainly due to absorb the water on clay particles. Okay, and on the static loading, maybe unloading only one or two very simple cycles. Okay, but on the cyclic loading, I believe that's another factor we have to consider. You know why? Because cycle loading, you can loading more frequently. You can change the particle orientation, sliding orientation, which you make the particles getting closer and closer. And so I believe my model can be a basis for people to extend my model to consider a case on cycle loading. Cycle loading can contribute a little more, can add something more. But how to add? I tell you, I have no answer yet. But this kind of time, the strain rate is depending on the strain only. I believe so can also be applied to the behavior on the cycle loading. But I have no good data yet. You can verify, especially for people in NGI, you deal with the behavior on the cycle loading. Probably you can have a further study. Probably the viscoplastic strain rate maybe is also dependent on the strain state. Can be a basis, but I believe cycle loading can add another factor because cycle loading can make particle sliding, rotation, blah, blah, maybe can add another factor, but I don't know. I cannot give you an answer yet, okay? Thank you very much for your very good question. I saw this question before, I tell you.
Think about it, because I've seen this behavior in centrifuge, but things like that's not really my research area, so that's why I just let it go. But you're the expert in CRIP seems, so that's why I'm asking you.
Yeah, good question. For sand, you can imagine for the sand. Okay, people do cycle loading. Then the particle can get closer. We can have a liquefaction. Because on cycle loading, particle can get closer than generate some additional pressure liquefaction. And
I'm not talking about sand. I'm talking about pure clay.
I know. You're right. I mean, I just borrow some studies from the cycle loading on the sand. For clay, maybe have some similar effects. I really have no time to study this issue yet. Okay. Yeah. Okay. Thank you very much for your very good question, which you need further study. Yeah. And so you can see my models here. Nonlinear rheological model are very similar. You can see the strain rate. This is elastic part. This is visco plastic part. My visco plastic part. But my model is nonlinear. Maxwell model is linear. Not good for soils. I mentioned before for the odometer test. The Maxwell model give you, a wrong answer. I tell you, because the behavior of the soil in odometer test is nonlinear. Okay, I'll go quicker. Okay, otherwise I cannot finish my talk. For 45 minutes. But I will control my time. Okay, don't worry about this one. Okay, I have a number of very basic papers published already. You can see if some people are interested in this one, you can read. No need to go this one. Odometer test. I tell you what I'm discussing next is how to derive this one-dimensional elastic visual partial model based on my concept. I don't know. I don't need to go details. And all of my concept models can be derived state by state by state. And you can see based on this model again, you derive. Very important is how to divide the strain rate into 2 atoms or 3 atoms or 4 atoms. In my study, I believe I divide into only 2 atoms. Total strain rate divide into elastic strain rate and viscoplastic strain rate, 2 atoms. Some people, you can read the paper, some people divide this into 3 or 4. I don't know. But to me, only 2 atoms are good enough. Okay. Then how to derive each atoms? Following a few slides can show you state by state. But based on my concept, everything can be derived. Okay, on the slides or on the paper. That's a building. So my concept model is not a curve fitting. It's not the empirical relationship. It's a really logic, the theoretical models, okay, derived. And also I want to say is this one. You can see some curves here, like copper line, chemical model, blah, blah. And elastic plastic line in chemical model is the lambda line. They normally consider in the local scale is a linear. Okay, I'll show you this one is better. Or in the local scale, this is a copper line, this one is a lambda line is a linear. If for some sensitive clay, I know the NGI people study sensitive clay. When I was visiting Helsinki, Professor there also mentioned to me the sensitive clay. Sensitive clay is not really a straight line. So some curves and blah, blah, blah. Okay, it's different. Based on my approach, based on my framework, my concept, you can use a different curve. You don't have to use a linear local function here. You can use a curve function here. You can derive your own constitutional model based on my approach and my concept. That's the beauty of my model. My model is a framework, is a concept. Actually, you can derive your own model very easily. I tell you, we did it for other cases, but I have no time to show you. So for sensitive clay, this here is maybe it's very hard in the curve in local scale. You can find a proper function to fit that. Then based on my concept, you can derive your own elastic nonlinear, okay? Elastic viscoplastic model, okay? That's what I want to say. Okay, my work can be a basis, okay? I go details, I don't go details, okay? All the details here just to show you how to derive. I want to skip this one. So finally, I can get this elastic viscoplastic model. You can see this part is the elastic strain rate. This part is viscoplastic strain rate. That's so simple, derived. Okay, I don't go to details. How to determine parameters? You can use a rigorous way or simple way. I want to skip. I want to skip. One thing is for engineers. Engineers people know conventional parameter very well. So that I try to link the model parameters in my model to the conventional parameters. So engineers can use it easily. For example, sorry about this one. For example, CR is an elastic index, compression index, or unloading index. CR is related to cover. And the compression index, CC, related to lambda. The secondary consolidation coefficient, CRV, related to percent. V is 1 plus E0. So all the models in my model, all the parameters in my model can be related to conventional parameters. So engineers can determine the value of the parameter very easy. This is what I want to say, okay? What I want to say. Okay, here, I'll go back to cyclic loading here. You see, the real behavior is a loop, unloading, reloading. But we simplify it as a line. It's a simplification. So how on the cyclic loading, where the nugget is a loop. Loop even on the cyclic loading, the particles can getting closer, even for clay, closer. I believe cyclic loading contributes additional influence on the behavior, but I haven't done work on that yet. I believe if some people have time, you can try to extend my model to consider cyclic behavior based on your data, but I have no time to do it. My model, my concept, my framework can be a good basis for you to work on, okay? That's what I want to say. And verification, I don't want to say that one. Of course, verification. When I was a student, I was young. I studied in the wrong, my lunch. My supervisor, Jim Graham, I mentioned before, he did a postdoc at NGI. Like you're doing postdoc. So it's a good experience for you, I tell you. 10 years, 20 years here, later you will appreciate for the hands, okay? Who gave you the guidance, okay? This is my supervisor, Jim Graham, very nice guy. He taught me how to drink whiskey in the airplane. He's Irish professor. A photo was taken in the Niagara Falls, on the board, Niagara Falls. We went to an Indonesian conference, very good experience, okay? And hypothesis B, hypothesis A, I don't want to go details because I have another talk on Friday. The two different hypotheses for sediment calculation, I skip this one. And very important thing is my original contribution was appreciated or recognized by Geotechnic. Probably you know that in 2008, Geotechnic published a review paper. For all the paper published in the past 60 years, they select some papers they consider which made contributions, milestone contributions. And my paper was actually selected, and they give a very high remarks on my model. You can see equivalent time, okay, how is the model of Ian Graham. Actually, this is a consolidation, is an application of my one-dimensional elastic viscoplastic model in consolidation problems. The paper itself is not a constitutional model. It's apply my elastic viscoplastic model to consolidation problem, which is published in Geotechnic. And he said this model introduces equivalent time concept. Actually, Professor Dr. Barron's paper mentioned equivalent time. Okay, it's not the original for me, but I give a very clear definition of equivalent time. That makes a step forward to modern creep. So my contribution, my model make a step forward. Okay, it's a good step forward. Okay, in this area, and they have more. Well, I just sign a little bit. Okay, I don't work on this one. Later, I extend the one-dimensional to three-dimensional. And how can you extend this one-dimensional model to three-dimensional is also based on previous work. Number one is the Pizarro's work, 1966. Okay, Pizarro's work. Second one is the modified chemical model. A chemical model cannot consider creep, but it's a very good elastic plastic model. It's a framework I can build my model. So everything I presented here, I say it cannot solve all the problem, but can be a basis for you to develop other models. You know what I mean? Including myself, I develop my model based on other people's work. Okay, so you can see this one, Pizarro's work, modified chemical model, and my one-dimensional model is the basis. Okay, based on three, I can derive a new model. I don't go details. The actual three-dimensional model is this equation. It's here. That's it. I don't go details. Okay, today 45 minutes. I remember that. And we also apply my model to solve consolidation problems. One, actually, I want to mention to here. I mentioned to you that on the cyclic loading, the sand can generate additional pore pressure within generate liquefaction. So cyclic loading can generate the pore pressure. Another thing probably people don't pay attention is for the creep of the soils can generate additional pore pressure in soil soils. On the constant loading, the creep can generate additional pore pressure, which is a good example. Is this example in the artificial island on the seabed in Canada? Okay, in Canada, in the north of Canada, they did some measurement. You can see when the artificial island was built, the pore pressure at a certain time still increased, then decrease, increase or decrease. You know. According to Tarsaki theory, if the soil behavior is elastic plastic, the pore pressure should decrease from beginning to zero. But in the middle period, pore pressure increase. And people try to simulate this one. Okay, that's not, cannot do that. But I found this is another reason why pore pressure increases, not due to cyclic loading. Certainly here, not cyclic loading. It's not due to some other reason, it's due to creep. So my published paper to study this issue in 1999 explained this kind of pore pressure increase is due to creep. If you know how to do triaxial test, I tell you, very simple. You can observe in a triaxial cell. You can consolidate a sample, under say 100 kPa, let the water to come out, do the consolidation. When in the middle stage, you close the valve. Don't need water to come out. The confined pressure 100 kPa is kept. You don't need water to come out. The pore pressure in the sample will increase. Because soil has creep. The nature on this constant loading, creep. The particle tries to shrink, but the valve is closed. The volume change is zero. No volume change. Then they have to try to creep, but cannot creep. Creep means decrease in the volume. But the valve is closed, cannot decrease volume. Then the soil inside, particle inside will do some unloading. Then the effect just decrease. Effect just decrease. That what cell pressure 100 kPa is the total stress, is kept. Effect just decrease. Effective stress due to unloading locally, the pore pressure has to increase to balance external 100 kPa. If you don't believe me, you can do a simple triaxial test, do the consolidation. You close the valve, the pore pressure, you can measure the pore pressure on the top or bottom, doesn't matter, the pore pressure will increase. So creep is an independent mechanism which can cause the excess pore pressure increase. This is what I say. Cyclic loading is another independent mechanism which can cause the increase of pore pressure. Because cyclic loading, particle getting close, but has to shrink particle. But because so quick, the pore pressure cannot dissipate, cannot come out very easily, then we have pore pressure increase. It's similar, but totally two different mechanisms. One is due to cyclic loading, one to the quick. I published a paper on this issue, makes it understand very, very clearly. That's why I said that you ask a good question. Cyclic loading can be another factor comes to the tightening behavior, but I have no time to study it. So this is a good reason to explain to you. Another interesting thing is, praxis, right? Very popular in Europe. And the soft soil creep model, I can say this one. Actually, I didn't pay much attention on this one in my life. In my life, always doing the work, have no time to recall, to go back. And my students actually find out the soft soil creep model actually is very similar to my three-dimensional model, 95%.
Mm.
And I believe I published my three-dimensional model much earlier. Published in my thesis 1990, journal paper 1990, but Professor Peter Vermeer, not Dr. Nahan, I know Professor Peter Vermeer very well, and he published a conference paper 1990. So my work was done ahead, their work. But some people say, in practice, many consider models, they never mention the origin. They just use the model, put it in the model. Okay, so this the model in practice very similar to my model, but my model was developed much earlier, at least nearly 9 years earlier. Okay, in my thesis. Okay, just one example to show. But you use the soft soil creep model in practice, which is elastic, which is a three-dimensional elastic with a partial model. So it's good. It's good model. It's a good model. Okay, even my students use it. Because the conversion program very easy to do. If you want write your own routine, is very difficult. You know what I mean? Okay. So just go this one. I don't go details. One more thing is also related to bearing, and you can see the curve. Okay, you can see the curve on the high stress. Actually, the curve is not really parallel. It's getting close. You're not getting close. You can see here, getting close. Okay, of course, on the small stress range is parallel. It's okay, not too bad. For example, here on the very high pressure, the curve will converge. Okay, it's not linear because the watch ratio we cannot. At the most watch ratio reaches to zero. Watch ratio reaches to zero. So if we use a local function, watch ratio can go to infinity, or even go negative. Okay, this is a compression. It's not right. Another thing also mentioned, when the creep going down, if we use a local function, for example, this local function to fit the odometer test, you're in trouble. Okay, this odometer test, you see this local function to fit it. When the time is infinity, watch ratio can be negative. You can see time go to infinity, constant. This zero is constant. Okay, this go to infinity. This negative here is go to negative. Watch ratio cannot be negative. So this local function can feed the data in the small range. If you go a longer time, a large range, it give you wrong results. How to solve this problem? Okay, I tell you, I propose a new function which is very simple, can feed data very well. I go very quick. It's a combination of a hyperbolic function and local function. So simple. I spent a few years to figure out a good function. Okay, you can see hyperbolic function has a limit. Local function no limit, but local function can feed the data for a certain range very well. So I combine local function with the hyperbolic function put together. Oh, it's a beautiful function to feed this nonlinear behavior. Based on this new function, I can also derive a new elastic visco partial model. So I actually share you some experience with you. I published a very technical note in Geotechnical, actually, which is highly cited. Okay, really highly cited. Okay, 1999. It's a good function. And some people have extended my work for different areas. I don't go details. Just a simple methods I will cover in Friday. I don't cover here. Okay, I don't cover here. I'll give more time for you people to ask me questions. 45 minutes. Okay. Oh, sorry, it's a little bit beyond. And now I want to draw a conclusion. Okay, the number one, creep strain rate, which is the viscoplasty. Okay, is depending on the strain state only. Once you know strain, stress here is the effect of stress. Then creep strain rate or viscoplasty strain rate is fixed. Nothing to do with the loading path. Okay, that's what I mentioned to you. Based on Barron's diagram, I explained this observation. In Graham's one-dimensional model is a good rigorous extension of Maxwell's linear rheological model. I say it's rigorous because based on concept, understanding the framework, I can derive this model by hand. No fitting, it's not empirical. Use the same concept, the same framework, you can derive your own model. So it's a framework, it's a concept, okay? My three-dimensional model is a good extension of the modified chemical model. Chemical model cannot consider viscosity of the soils, but my model can consider. In my model, when the viscosity parameter becomes 0, my model automatically shrink, reduced to the modified chemical model. It's consistent, okay? And I also suggest to you a very simple nonlinear function to fit some good data with some limit. Okay, overcome limitations of some functions. Local functions give you wrong results on the large stress for the longer time. Some errors. Okay, I can overcome those limitations. More verification extension applications have been done by others, which demonstrate validation and usefulness of concept or framework. Other people have extended my model to other situations. You can do so by yourself. Okay, my model is not empirical, and many people made contributions to my work. I want to acknowledge. Due to time limit, I don't read. Okay, thank you very much for your attention. Thank you.
Any questions?
I will
Go
definitely
the one.
Can I have one first?
Oh yeah, Professor has. Okay.
Is it okay for you?
Yes, of course.
Since
For
you
you,
have the
anytime.
first one before, so I have the second question. First, in a way, thank you for your presentation. Of course, everyone that has been looking into creep has been looking also into your papers, so they give, of course, a good background for, in a way, understanding creep behavior. So I was, in a way, reading your papers, your initial papers. And of course, Bjerrum, we are reading, of course, and looking, and this isotac concept of Bjerrum is, of course, extremely important. So that is the background, I think, of most of the models used today, that at least a lot of people believe in. But into this, and also into your models, we wanted to study this concept by laboratory tests. And of course, we have this creep, you're going downwards there, and of course, we're talking about 300 years and 3,000 years. In a way, we cannot wait so long. So what we was doing is that we was doing a creep test, and we was doing it in in a Jianhua test to keep, in a way, also have control of the keynote, because in a way, if you are in an odometer, you don't have control of the keynote. So we was creeping for 1 year. And then we wanted to check this, whether we can find these isotac lines by unloading.
Okay.
So
Should it be the same?
So same as you say there. Yeah. So we had, in a way, find all these creep lines by having one test creeping for 1 year. Then we started at the same point, starting to do different unloading to different levels.
Unloading,
and then measuring the strain rate of the different amount unloading.
Yeah, good idea.
And we was doing that, and in addition, we had an odometer curve, or also that Jianhua test to measure, in a way, the non-linearities of this. So in a way, this lambda value that you say is not linear, we also found the non-linearity of that, and looked into this kappa value at different unloading steps. So in a way, we were finding all the parameters and wanted to see whether this is fitting together. And I will show it to you, and we can discuss it later, because we have all this data. But in reality, it didn't fit perfectly. It is some questions we had. We needed to modify some of the parameters, and we don't have explanation why we needed actually to modify. And it was, first of all, the lambda value that goes into the strain rate that actually needed to modify due to unloading. And no explanation why.
Very good question. Okay, very good question. According to my concept framework, from unloading back to the same point, strain rate should be the same. But you said sometimes not exactly the same. Probably one of the reasons is come back to the cyclical unloading.
No, but it is not cyclic. Just unloading.
Loading.
So in a way, it is just exactly like this. Say that, okay, it's a little bit same to what you say there. We was having one test, creeping to this line.
Yeah, you can get a strain rate.
Then we was unloading to this line
Okay.
and looking what is the creep rate there
The same.
compared to the creep
Okay,
rate
okay,
there.
okay, okay.
And we was doing that at different levels because we had a creep test that was quite long, and we was unloading to different levels, measuring the strain rate there, measuring the strain rate there,
Okay.
and by that seeing whether this is fitting together.
Okay. Very good question. Number one, okay, isotag model. What the mean of isotag is the line with constant viscoplastic strain rate. So the line with a constant viscoplastic strain rate. Many people, or some other people, develop a model based on this one. Actually, isotag model, but equivalent time model is the same. Is the same. Okay. Okay. For the same timeline. The viscoplastic strain rate is the same. Corresponds to the same viscoplastic strain rate is the same. So in this regard, is the same. But some people wanted to get viscoplastic rate first. By the loading or unloading, as Professor Amperes mentioned. But for me, I want to do the creep test first with the time, so we can get this kind of different timeline to fit this one to derive a differential equation to get the viscoplastic. Now, go back to your point. So he just want to do another different way. So do the unloading to here, then on the same water node to keep it to measure viscoplastic rate. You can do this. But you can also do the creep test from here to get the rate. You mentioned maybe not the final viscoplastic rate, not exactly the same. Yeah, you're right. But according to my theory, my model is supposed to be the same. Supposed to be same. Why is not is different? It's possible. We have to think about it. One possible reason is still related to unloading, because this one, you want to go here, you need unloading. Unloading, the clay particles I mentioned before, it's not a line, perfect line, is some loops, which may be that's another contribution factors to this one. But how big is this factor? I don't know yet. So you know what I mean. So we have to think about this one. We need some further studies. I agree with you. Okay. According to my theory, it's supposed to be the same, but in reality, not exactly the same. So we need some time to think about it. Thank you very much. Okay. From online, one.
Hi. Yes, I'm fascinated about Hong Kong, especially you guys having so many of a reclamation project. So like in terms of estimating creep is, I guess, is very important. I guess, you're dealing with a lot of real infrastructure works and, settlement control, this and that. So in terms of your study and your research area, what is your recommendations for the engineering practice these days in terms of foundation selections, dealing with settlement, differential settlement, connecting existing infrastructure to new infrastructure? You guys recently have the third runway. How maybe you can use that as an example to give us some insight to dealing with that creep related to the secondary consolidation problem.
Okay. Number one, many people consider creep is a small thing, contribute very little to the settlement. And people say, is the elastic plastic deformation contributor or not? This concept is wrong. Okay, I want to correct that one. I want to go back a little bit related to settlement. I will answer all your questions later. Okay. One very important mistake, misunderstanding is people consider creep is small. Elastic plastic is big. And people say, for example, for this I want to show you. People say for the loading to here, on the certain loading, for example, from 1 to 2, from loading to here, then come to here, okay? This is according to KMK model. This is the number line. So then this is settlement, okay? We need to settlement. The creep here is small. This is a very important concept. People, this is a reference timeline. Is a lambda, is the elastic plastic line. You load from here to here to here, then this is compression related to settlement. Here further is small. In reality, this is wrong. In our elastic with plastic theory, the true instant deformation, on the elastic from 1 prime to here is actually very small. All here from 2 double prime to here is all creep. occur so quick. Maybe from here to here occur very quick, maybe a few seconds, maybe a few minutes. It's so quick. You consider it's instant. In fact, according to my theory, it's an elastic it's a viscoplastic. It's a time dependent. You know what I mean? So actually the visco sediment, according to elastic viscoplastic theory, instant compression is small. Time dependent compression is much bigger. Can be 90%. 80%. Okay, number one, okay, regarding the sediment component. Number two, I remember your question. For the structure on the soft ground, creep is important. How to choose the foundation in Hong Kong, okay? In Hong Kong, because we have so many tall buildings, the load of the building is so huge, so we have to use the piles. And we install piles, on the rock surface. In most situations, we install piles in the rock socket. So we transfer the loading for the building all the way to the rock. You know what I mean? So the sediment of the building is very small. But
in terms of that, gaps
yeah,
in between. The gaps after the foundation is not settling and your ground is also settling at the same time.
Yeah, that's a good point. Yeah, that's another point. I mentioned before. Even though the building supported by piles, sediment is small, but we still have soil surrounding. We still have other like pavement, maybe other pipes which are buried in the soil in the field. Field is supported by soil ground. You cannot build piles to support the pavement. It's expensive. It is not really support on the piles. So sediment of the field or the pavement of pipes on the newly reclaimed land on the soft soils underneath can have sediment. And that's a big issue. That's also a headache in Hong Kong. Once we have groundwater drawdown, in many cases, due to the constructions of water drawdown, which can cause very significant sediment. And some sediment, especially for new reclamations, some sediment will last for a long time, maybe 20 years, 50 years. The sediment is the issue. So in that case, the ground improvement before construction is important. So you have to make the soft soils underneath strong. Use different technologies like water drains, compaction, sand, piles. In some cases in Hong Kong, they use mixed cement powder with soft soils, make the soft soil strong. The purpose is to reduce the sediment for this soil ground, not for piles. Piles is not a big issue. Piles are supported in the rock socket. Is that okay, my answer?
But do you think it would be a better idea if you can say drag out of the area and make it shallow foundations, make it settle together with the connecting adjacent land? Do you think that's probably better and cheaper compared with piling?
Shallow foundation is not very commonly used. Occasionally used shallow foundation. Yeah, shallow foundation is, even though shallow foundation you have a large spread area is good. But to support the tall buildings is still difficult. So in Hong Kong, for tall buildings, people never use shallow foundation. Maybe for 1 or 2 stories buildings, especially for temporary buildings, shallow foundation is a good answer. It depends on different buildings. But in some cases, it's like a runway. Hong Kong runway can be considered kind of shallow structures. In that case, you go ahead.
Does it mean
shallow foundation, like a mat foundation, normally support the low-rise buildings is okay.
So
but not
it
for tall buildings.
The third runway concourse can be proposed as a shallow foundation.
For water buildings.
Yeah. Sorry, see, the canteen will be closed, so if we have further questions like Kuwa and
then anyway,
we can take them. Maybe we can find another time. For
yeah. We can find another.
Friday, I have another talk. We'll discuss more on sediment. Okay. Friday, I hope you can come.
You can meet physically on Friday.
Yeah. Okay. Thank you.
Thank you very much. Thank you. Okay. Thank you.
Thank you.
Okay. Thank you.
Yes. I already had learned.